Let's get slowly started. So thank you everyone for coming. We're going to be talking about Flink. My name is Kostas Zoumas. I've been with Flink since it was not called Flink. I'm co-founder and CEO of Data Artisans, the company that is basically supporting the project. Let's start with the obligatory, who has heard of Flink here? All right, very nice. So we're going to be talking about Flink, and we're going to be talking about streaming. So there are actually two Flink talks in this conference from our company. One is today. This is going to be a less technical talk and more about how several companies are using Flink and what can it actually do for you. And there is going to be a much more technical deep dive on Thursday. I will share the details at the end of this talk. So first of all, let's start with what is streaming. Yeah. So there is a big movement going on right now with streaming technology. And in my view, this is because people are simply realizing that their data is continuous. Yeah. So most of the big data sets are continuously produced, and it just makes sense to consume them and process them continuously. So we're really talking about the obvious thing here. Before, there was a technological gap, so the tools to do that were not mature enough, so people ended up using tools that were not tailor-made for this purpose, or building their own. But now the technology has actually matured. So what I'm saying here is that you are probably, if you are doing lots of things with data, you're probably already doing streaming. You might not be using streaming technology for that, but you really should. And why streaming? So with working together with a number of companies that are using Flink, we have sort of observed that there are a number of drivers to adopt streaming technology as central in the data infrastructure. And for many companies, it's one of those reasons. For other companies, it's all four. Yeah. So the first one is being able to monitor your business in real time. So this is extremely valuable. So what is happening, continuously in my business, and being able to react to this also in real time. Yeah. So if I see an anomaly, I would like to know it now and react now rather than tomorrow. The second is what we call continuous applications, and especially implementing these continuous applications robustly. So these don't have to be about real time, but they are applications that are running continuously 24/7. You depend on them, and they never stop. The third driver, that's popularized by large Silicon Valley companies, and now it's being adopted by a very large subset of the enterprise. It's all about microservices, adopting a more decentralized architecture. And then if you actually do that and look, what does this mean for my data infrastructure, for my backend, streaming is a perfect match for that. And the final is basically consolidating the whole infrastructure for doing data analytics. So instead of throwing 200 systems at it with specialized systems to do fraud detection, specialized systems to do SQL, specialized systems to do social media analytics, et cetera, you can actually consolidate a lot of this using one platform underneath. And I will talk about exactly these 4 points in this talk. So the first one is about real time. So a common misconception in the industry is that streaming and real time is the same thing, and they're really not. And you cannot even say that real time is a subset of streaming, or streaming is a subset of real time. So there are streaming applications that are definitely not real time. So you are computing, let's say, time windows over a day, and you're doing something over these time windows. That's a continuous application, but it's not real time. And then there are real time applications that are not streaming. For example, you're doing ultra fast queries on a data warehouse. That is most definitely real time, but it's not streaming. However, streaming is a very nice way to implement applications that need real time responses. So for example, with Flink, other people have benchmarked Flink, and we have benchmarked Flink as well. So for example, there was this Yahoo benchmark a while ago that measured Flink, Storm, and Spark, and basically clocked Flink that very low sort of millisecond latencies at the 99th percentile, even with the throughput going up. And we have even extended that to a much larger scale. So basically my point here is that using a stream processor like Flink, you can do things like millisecond response rates. And that is useful in several cases. So for example, one of the earliest, so why does this matter, right? So one thing is, immediately react to events. Yeah, so there are a number of events happening in your company, for example, in your infrastructure, and you want to monitor that. And whenever you see an anomaly or you detect a pattern or you detect a special event, you want to generate an alert. Now, there are cases where this is not crucial. So there are several applications that are not latency critical, and there are several businesses that do not depend on millisecond response rates. However, there is still a huge benefit of using tools that give you that because you avoid unnecessary trade-offs. So for example, in the past, in stream processing, people had to use between a low latency system or a system that would give you consistency. And these trade-offs are really not necessary. They were just the artifact of the technology not being there. So the cool thing about Flink is that it really brings you this low latency. It can sustain high throughput, and you get data consistency, what people call exactly once processing. And you get all of that as a package with not really a trade-off. Yeah? So even though if the applications are not to the millisecond, this actually matters a lot. One real-life scenario is from Bouygues Telecom. So Bouygues Telecom is one of the largest telcos in France, and actually one of the earliest users of Apache Flink. And they have built a system called Lux. They've been running that in production for over a year now. That basically has Flink in the middle, ingesting from Kafka, and it's used for diagnostics and alarming of their infrastructure. So for example, if something is going wrong at a tower or the signal is dropping, this creates alerts that end up to the network engineers. The system is used for other things as well. It's used for continuous BI, but this real-time diagnostics and alarming use case is a latency critical use case. So what they could do basically is sustain all the throughput that they need and get an end-to-end latency, including Kafka and Flink, of 200 milliseconds. So that was really the only sort of solution that they could use. All right. So the first thing was reacting in real time. So even though lots of people equate streaming with real time, for me that's really the tip of the iceberg. And things really get interesting when you're trying to implement robust continuous applications in production. So what does this mean? Yeah. So I'll call it a continuous application. It's an application that is consuming data, so it's a data application. It has to be live 24/7, and it's probably feeding other systems downstream, or it may be even feeding something that is user-facing, yeah, so a website, an app, etc. And it comes with certain requirements. So these applications need number one to be efficient. So you probably don't want to pay, give all your money to your AWS bill. They need to be consistent. So if you are counting things, aggregating things, etc., you need to be guaranteed that these things are correct, even if you have a failure. They need to be correct. So in particular, all of these applications sort of consume time series, so events that are associated with time. And being able to correlate the result with the time that it actually happened in the real world is extremely important. And finally, we're running this in production, we're running this at scale, we need to manage it, right? So it's not just a one-off sort of thing that I run it, I wait for the results, and then it's done. It's never done. So I need to be able to update my code, I need to be able to do maintenance, et cetera, et cetera. And stream processing in general is actually a fantastic way to implement these continuous applications robustly. Stream processing is not the only way to implement this continuous application. So in the past, and a number of organizations in the present, are implementing these continuous applications with batch processing, which means that I have a continuous ingestion pipeline. I'm getting all my data, and I'm splitting it up in chunks. Yeah, so I'm writing a file per week, or I'm writing a file per day, or I'm writing a file per hour, whatever my granularity I would like it to be. And then I am scheduling these batch jobs on top of these files. These files might be named like begin time, end time, something like that. So I'm scheduling these jobs on top of them. Hopefully, these jobs are going to be scheduled when the file has been finished, and hopefully they will be done when the next file is ready. And then that goes to whatever is my front end, so some kind of storage or some kind of serving infrastructure, etc. And people have been doing that with Hadoop and Hive, etc. For years. Lots of companies started with doing weekly batches, then they moved to daily batches, they moved to half a day or 3 times per day, and then they try hourly, et cetera, et cetera. So there's an ever-increasing quest to sort of make these batches smaller, which is really about getting results earlier and being able to react on them. And then the next idea was to actually couple that with something that is very low latency and it's running at the same time. This was called the Lambda architecture, basically inspired by Apache Storm, where you have the same thing running, but at the same time, you also have a streaming job. Now, because you're using Storm, you're not guaranteed that the results of your streaming job are correct, so they are approximate at best, but you get some kind of approximation now. And then you have the batch job at the end of the day that's going to give you the final correct result. Yeah? So this has been deployed very successfully. It does come with a bunch of problems. So there are a lot of systems that are being involved in this computation. It's not such, if you think about it, right, it's not such a complicated computation. We might not be doing any kind of fancy machine learning here. We might just be aggregating some data, right? And we have something to ingest, then we have a file system for the files, we have these jobs, we have a scheduler, then we put a stream processor again, and managing this stack actually becomes quite hard. And since if you're doing Lambda, you have to implement the same application logic on your batch processor and on your stream processor, and hopefully this will have the same bugs, but probably they will have different bugs, right? So that's a problem as well. The second thing is that we are treating time implicitly. So all of this is about time series, right? And what we're doing is we're saying, OK, we're going to write sort of hourly batches. Yeah? And what if we want to move from hourly batches to half an hour or 15 minutes? Yeah, the changes we need to do is basically all over the place. We have to change our scheduling. We have to change our jobs. The behavior of our jobs is different. All of a sudden, we have jobs that are much shorter but are scheduled much more often, et cetera, et cetera. We are constrained in this regime of very well-defined batches in these files. So if an event comes to the next batch, but it actually belonged to the previous batch, there's not really an easy way to handle that. Yeah, in most use cases, people just hope it doesn't happen, but in the real world, it happens more often than it doesn't, right? And finally, we are very constrained on these boundaries of the computation, right? So what if we don't want to do like hourly batches or minute batches, but we want to do sessions, right? So we want to see a user session, a user logged in, and then they either left and visited some other website, or they did something. Yeah, so these things become very, very hard. These things become very, very easy if you actually do continuous applications with streaming. So basically, the architecture is simplified radically. What you need to have is some kind of input, for example, Apache Kafka to buffer the data, and then a stream processor, so a streaming job that is running continuously, and it's basically doing the processing when new elements arrive, for example, with Apache Flink, and then you're serving or storing infrastructure. So it just becomes much, much simpler and much more robust. And an example of that is so after the Yahoo benchmark came out, we worked on an extension of that of several points. This was work of Jamie Greer, who is sitting right here wearing a Flink t-shirt. who before joining us was at Twitter, where they had a very similar continuous application. So this work was inspired by that. So essentially, what we did there was the following. So we want to do something that is very simple, which is count things. Yeah. So for example, count tweet impressions or count ad views. That was also what the Yahoo benchmark is doing. And this sounds simple, but actually the vast majority of analytical use cases are counting or generalizations thereof, like aggregations, etc. So if you look, for example, at anomaly detection, it's basically counting, summing, and then dividing, creating averages, creating standard deviations, etc. So it's basically representative of many, many real-world use cases. And because it's a continuous application that is serving downstream systems and we are depending on it, there are certain requirements that come with it. Okay? So in that particular case, the first requirement was performance. So we actually have millions of events per second, and we have millions of distinct keys. The second was correctness. So basically, these counts are always correlated with timestamps, and we want a window and count based on the timestamps that things actually happen. So things, the time that I clicked something, that I tapped on something on my cell phone, rather than the time that some machine in my data center is measuring, right? The third is consistency. So we would very much like to be correct here. Yeah. So we would very much like to not overcount and to not undercount, even if we have a failure. And the final is manageability. So this is a production application. I need to be able to pause it, restart it. I need to be able to go back and reprocess data. I need to be able to update my code, have planned downtime, et cetera, et cetera. And before Flink, the application could meet some of these requirements. So so we basically implemented that with Storm and Flink, right? So with Storm, you would need thousands of cores to sustain this workload. You might be able to, but you just need a hell of a lot of hardware. You can handle time in application code. Yeah, you might be doing that correctly, or you might be doing that wrong, but it would be a significant investment. Essentially, you're implementing half a stream processor in your application code. If you are using Storm and kind of a lambda architecture, you're not guaranteed that your results are correct. So they might not be correct during the day, but then you have a batch job at the end of the day that is giving you correctness. And basically, in this use case, the manageability requirement was met. And the difference with Flink was that, number one, you can basically sustain the same workload in tens of cores rather than thousands of cores. Yeah. That is important for a variety of reasons. The first reason is if you do have this kind of millions of events per second requirement, then you don't have to pay all your money to AWS. If you don't have this kind of millions of events per second in your business, you can actually implement more use cases. Yeah, so it doesn't have to be only fraud detection. You can also do marketing, et cetera, with the same cluster. You can tackle larger problems. You can perhaps start logging more. So you just get the ability to handle larger problems in less hardware. Because of Flink, time is correctly handled by the framework. So you don't need to do that in the application code. You do get correct results without needing a lambda architecture. So the stream processor itself does give you consistent results in the case of failures. We actually, while going through this journey, there were a number of features that we put in Flink in order to satisfy the manageability requirement. And there are some of those that are actually coming up. And these are extremely important for real use cases. Just before I get there, the results of this, they're public. They are in a blog post at dataartisans.com/blog. So Storm basically clocked out at about 500,000 events per second. Flink was clocked at about 3 million events per second, where the bandwidth of the network between the Kafka cluster and the Flink cluster became the bottleneck. By removing this bottleneck, we basically moved the data generation inside the Flink cluster. We could actually clock it to 15 million events per second. Plus, you get consistent results. And this is the Yahoo benchmark itself, right? And since publishing that, I am not aware of this being beaten by anything else. So one thing that we added for this manageability requirement that is extremely important is save points. So Flink has an internal mechanism of taking checkpoints of the application state periodically, just that it can guarantee to you this consistency in the case of failures. Now, one thing we did, and that is released in Flink 1.0, is basically giving this as a feature to the user as well. So as a user, you can say, take a snapshot of my application in state right now and just put it somewhere in a folder, for example, in HDFS. And that gives you the ability to go back in time, anytime in the future, and continue the application from that point, yeah, and while the results being consistent. So no data loss, no overcounting, no undercounting, nothing, yeah? And that is basically the building block that you can use to do so many things. For example, updating your code, or even running 2 versions of your application at the same time next to each other, comparing the results, or debugging, right? You maybe don't want to start from the beginning of time. Planned downtime, so you want to migrate to a different cluster, right? You wouldn't want to start again from the beginning of time, et cetera, et cetera, et cetera. So it's just a super useful tool to do all of these things. And there's a lot more coming up in this department. So Flink 1.1 should be coming out very, very soon, which has a lot of work for integration with metrics systems and monitoring. And Flink 1.2 should be the one after that, which actually gives you the ability to scale your applications at runtime. So while the application is running, you can give it more resources or less resources, and it will actually rearrange the state and continue as if nothing happened. The third point I had mentioned was a decentralized architecture. So there is a connection between microservices and streaming. It's in my opinion, an indirect connection, but when you are adopting such a distributed architecture, you realize that having isolated applications that have local state and are communicating with sort of a data flow concept between them is a much better match than having a global view of the world in a database and having to query the database whenever you need something. So one example of that very recently was from Zalando. Zalando is, in case you don't know it, it's a company in Europe, one of the largest fashion retailers. It's a very, very large tech company. It's a public company worth billions right now. Basically, the next slides are from what they have presented on how they're using Flink. So what they did was basically transition from this classic monolithic architecture where you have, lots of databases and then a big ETL process that puts everything in a data warehouse, and then you do the analytics on the warehouse, et cetera, to an architecture where, each team is building their own application with their own data store. Each team is doing their own ops, et cetera, and then they have basically an event bus that is connecting all these applications together. This event bus was implemented by Kafka. And then the next thing is, okay, how do you do BI on that, right? Do you follow the same approach of having a big ETL to a data warehouse, or is there something better? And the way they ended up doing that is exactly with stream processing. So they have basically a second Kafka bus that is basically in their backend. They're using a lot of Japanese words for their systems. I don't know why and what is the naming scheme exactly. And then they're using Apache Flink to basically continuously process this data in Kafka and also export this data to their data lake, which is in S3, or to basically export this data, so implement the ETL process to the data warehouse, et cetera. So you don't have to get rid of your data warehouse, but a lot of the logic can actually become logic in the stream processor. So few things that they are doing or they're planning to do. So the first thing was business process monitoring, which is basically, I mean, this is a website where you buy clothes, right? So you click on something, you buy something, and then a package comes to you, right? Or many packages. Yeah. So the first thing is checking, does this actually work? Yeah. So when someone bought something, did they actually get the same exact thing delivered to their house? So this is basically, how fast are things being ordered, when are they shipped from the warehouse, et cetera, et cetera, et cetera. And measuring SLAs of all of these things. ETL, I mentioned it, so all of this whole process of moving data to the warehouse. And some of the things that they want to move to is basically complex event processing, which is essentially reacting to patterns. So what happens if there's this kind of order and there's this kind of order, and then my warehouse tells me that I'm out of the shoes, etc. And sales monitoring. So monitoring your sales in real time. Just a couple of use cases. Microservices. And the last thing I want to talk about is basically consolidating analytics, which can also be referred to as stream processing as a service. It's not my term. I took it from a presentation from Netflix recently. Which is essentially what is the next step after all that, right? So how do we make, there's all this very powerful stream processing technology. How do we make it accessible to more and more people? So basically, how do I make my data scientists in my company able to use this kind of stream processing? And there are two things that we need to solve. We're working on them. The first one is basically make the interfaces much more familiar. So one thing that we did recently was the first version of SQL on both static data and streams in Flink, which this first version will be released in Flink 1.1, and we will continue to very heavily work on that. And the second thing is basically easier deployment of stream processing jobs in the infrastructure. So the data scientists should not have to really worry about that. So one example of that, using Flink, is a system that King.com made for internal consumption. So King.com is a very large mobile games company. They make Candy Crush, among others. So what they did was a system called Arbea. This is also from a blog post that they have published, which is basically a platform to make stream processing widely accessible inside the company. So the way it works is that data scientists just visit a web frontend and write up a script in Groovy. And then there is a whole backend of using Flink that executes the scripts. And the way they're doing is actually extremely interesting. So they have streams of data coming in, and when a and then they also have a stream of queries. And they're basically joining the data with a query. So when a data scientist puts a new script, that becomes a new event in the query stream and is joined with a data stream. So you can actually sort of use the same Flink job to answer a lot of queries. You don't have to, but you can. And I hear that Netflix is trying to do the same thing. So Netflix recently, this is just from a talk that they gave recently at Data by the Bay. They're planning to offer stream processing as a service internally. They are starting out using Flink and Apache Beam. But they are planning to also support all sorts of other stream processing engines underneath. That was a very short talk. It's good. We can open for a very long Q&A. Just to let you know, so first of all, a disclaimer. Obviously, that's a lot of that was not my work, but the work of very talented engineers in a lot of these companies. I don't have the full list, but I promise that before I publish my slides, I will ask them and get the full list of people. I thought that a sample of what people are actually doing with a framework would be helpful also for others to see what are the possibilities and what can I do. There are two more Flink-related talks in this conference. The one is tomorrow by Alibaba, where they are presenting a system called Blink. So essentially, this is a fork of Flink that they have been using at a very large scale for a large period of time, and Alibaba now is basically trying, together with us, to roll back, to move back to the open source, so to sort of merge their changes back. And then the next talk, a much more technical talk, is on Thursday by Stefan Even. It's very interesting. It's called Turning the Stream Processor into a Database. So basically there, if you go, you will hear how you can use a stream processor and actually query that state online, so you can even obviate the need for a key value store. If you are doing stuff with Flink, there is a conference that is happening in September in Berlin, Flink Forward. The submission is in 2 days from now. The submission date may or may not be prolonged, so watch this website. And if you are really excited about the stuff as much as I am, and you would like to work with us, we're hiring. And basically, yeah, that's it.
What technology Flink uses for local state store? Like it's a Redis, it's a RuxDB.
So the question is, what technology does Flink uses for local state storage? You have 2 options right now. It can be either in memory or in RuxDB.
How do you replicate state management between nodes?
How do you replicate state management between nodes? So the state is generally local, right? So when you're doing, for example, a window, these windows are local. So you don't have cross state updates. You have a shuffling beforehand.
Yes, but in case if this processor fails,
Right.
the state has to replicate itself.
Right, so the question is, how do you keep the state fault tolerant? So the way Flink does it internally is by a mechanism called checkpoints. So every, let's say, 1 second or 5 seconds, you're going to take a checkpoint of the state or of the deltas to that state, and it's going to actually put that in an external system. So HDFS, S3, some other file system, some people are doing it in Cassandra, etc. So you don't, right now, there's no replication.
Will you guys be releasing 1.1?
Sorry, can you?
Have you released 1.1 yet?
1.1 is not released yet. I don't have a definite target date, but right now it's basically the last sprint, if you wish, to getting there. It shouldn't be more than a month or 2.
Do you have
About
a
it.
website with a quick start or anything?
Sorry?
Do you have a website with a quick start? Anything
There's a website on Flink, flink.apache.org. There's a quick start where basically you get to process the live edits of Wikipedia. So it will walk you step by step on building this kind of application.
What's the current status of supporting Apache Beam?
Apache Beam. So Apache Beam is a different project. Yeah, it's the ex Google Cloud Dataflow SDK, and it's now an Apache project that includes 2 runners. One is a Flink runner, and one is a Spark runner. So in the Beam website, there is actually a section where they say exactly which features are supported by its runner, and the Flink runner is at an extremely good state. So it is either on par or just a little bit behind Google Cloud Dataflow itself. You will probably not get the same performance as using Flink native, yeah, but there are no benchmarks on that yet, so I don't have a good answer to that.
Duplicate. So how does the Flink handle duplicate events?
How does Flink handle duplicate events? Short answer, it doesn't. So if your input has duplicates, right, and Flink does not know about it, so Flink does not have internally something that will check, that will buffer things and check every incoming thing with things that have come before, right? You can implement that as a Flink operator. What Flink guarantees to you is that when you have a stateful application, updates to that state will be exactly once in the case of failures. So if you're counting, then you're not going to overcount. And if you have an input stream from Kafka or Rabbit, and then you have Flink, and then you have a sink, if this sink is a sink that Flink can cooperate with, for example, HDFS or Cassandra coming up, then you're also guaranteed to have exactly once delivery to that sink. But if your input itself has duplicates, and Flink does not know about it, then there's not really much it can do about it, right? Sorry?
So in case of fault tolerance, let's take a case, your event is missing somewhere. Actually processed and resulted, but while sending the acknowledgement back, it failed you somewhere. So there is a chance that the event will be processed again, but the event is already there. So in this case, the duplicates can occur, right? It's not just the same event.
So yeah, so Flink, so in case of a failure, Flink will process your events again, but it will make sure that the state updates are exactly one. So the state updates are as if it did not process the duplicates again, because it will restart the input stream and the state to a consistent point. And it would also guarantee, if you're using one of these sinks, that in your output, your output will be as if the results were not processed again. The events were not processed again. So internally in its buffers, it might process again things, but externally in state or in output, you will not see that.
How would it resolve a timestamp instead?
Can you repeat it?
So the framework internally take care of some timestamps, right?
Yeah.
So in case of failure and in case of reproducing, replaying those events, how would it resolve the timestamp error?
So the question is, how does the framework handle timestamps in the case of failures, right? So first of all, so you as a user will tell the framework, for example, this field is a timestamp, and you will give it something that is called a watermark. This is basically a mechanism for advancing this event time. Handling this event time is completely orthogonal with fault tolerance. So basically, windowing and time handling is built on top of the fault tolerance mechanism. So there's not really a connection between these two. So the results will be as if no failure happened.
Can you talk a minute about the benefits of Flink versus Storm?
Oh, yeah, more than a minute. Sorry. Okay, so I think if you compare Flink with Storm, there are a bunch of differences. There are a bunch of user-facing differences and operational differences, right? So obviously one is the API. So if you can look at the Storm API, you can look at the Flink API. It might be a matter of taste. There is a compatibility for Storm in Flink, but it's not at the level of maturity for production as of yet, but there are people that are using it. And the biggest differences then are operational. So one thing is that Flink can just, our time is up, but very, very shortly, Flink will scale to much larger problems, with the same hardware, or much less hardware actually, and Flink will guarantee this exactly once consistency where Storm will not. Essentially, Flink is a stateful stream processor. Storm is not a stateful stream processor. Storm does not have, at least until the last version, does not have the mechanism of maintaining state. Sorry? Sorry, I should say that Storm 1.0 does have mechanisms. I haven't looked in detail, so I don't know what are the guarantees. But Storm 1.0 does have a state mechanism and windows, etc.
And just to add to the point, Yahoo does scale to 4,000 nodes.
So can you repeat that?
Storm does scale to 4,000 nodes. Yahoo does operate on
Storm scales to a lot of nodes, but
Yahoo, it's 3,500 nodes in total that we're running at. Our largest cluster, we'll talk about that later, is about 700, 800 nodes.
sorry, I think my point was more about efficiency, not total scalability. So how much you can do with one node versus how many nodes you can scale up. Probably Storm has been scaled to more nodes than Flink by now. All right, thank you. Hey man, how are you?